Hello, everyone. Today, let's have a look at the physical acceleration models in reliability engineering. So the idea is easy, but the implementation is very challenging. As you know, that today's highly reliable components, it's very hard for us to get enough data failures at the normal use condition. So, for example, a component might work for 10 years. I mean, can we test under normal use conditions when you wait for 10 years and then get the data? I mean, that's not how the reliability test is done today. So how can we make things happen faster? That means in reliability engineering, we are trying to make failures happen faster, and we're going to check how the failures at the high stressed conditions and how they are related to the product normal use condition under much lower stress. So this is called stressed testing. We have failures at a use condition and also failures at experimental conditions like highly stressed conditions. Okay, so normal use, stressed condition. So is it possible we can have a model that can model the physical acceleration of the failures? So the assumption is components operating under the right levels of increased stress have the same failure mechanisms as under normal stress. Basically, nothing has changed, but they are accelerated. So general physical theory. Failures may be due to mechanical, fatigue, corrosion, chemical reaction, diffusion, or migration, those kind of factors. So cause of the failures are the same. I mean, under normal use condition, under high stress conditions, only the time scale is simply different. Okay. So physical acceleration, operating a component at high stress, that is high temperature, maybe high voltage, high humidity, or high duty cycles, produces the same failures that would occur at typical use stresses, except they happen much quicker. So the first model that we can consider is a linear acceleration model, or we can consider that as a linear acceleration factor. So this one has practical application. Use simple multipliers of the time scale. That means time to fail at stress S1 equals to acceleration factor times the time to fail at stress S2. So the AF is the acceleration factor between stresses. So use condition, you see, this is a use condition time to fail, actually equals to the acceleration factor times the time to failure at stressed condition. So if we know the time is just accelerated, now how can we derive the failure probability, like the CDF function or PDF function or failure rate functions, because those are what we are interested in reliability engineering. So first, let's if the time is increased, okay? Use condition is just a factor times the stress condition, because stress condition you happen much faster, right? So you multiply by a factor, you get the time to fail at the use condition. Now let's have a look at the CDF function. FUT is the probability of failing by time t at a use condition, which is equivalent to failing at time t over f at stress s. So this is a time probability of failing by time t at use condition. This subscript u denotes use condition, s denotes stress condition. So for the same time, this one actually is t, however, in a stress condition, because it happens much faster, so we use t over af, because this is smaller time. So the CDF function, this is a relationship of the CDF function. So originally, the part is going to fail at time t, but under stress, it is happen much faster. So time t divided by AF, that is accelerated. Now, if we have this CDF function, because the PDF function equals to the derivative of the CDF function, so we take derivatives on both sides. So on this side, if you take the derivatives, it's FUT. On this side, if you take the derivatives, because you have another factor of acceleration factor here. So this is actually, you take the acceleration factor to the front. So 1 over AF, then FS T over AF. So this is calculus, from the calculus. Now, we got the relationship of the CDF function and the PDF function, because FUT equals to 1 over AF, FS T over AF. Now let's get the failure rate. How do we get this relationship? This relationship, because HT equals to FT over RT. Because FU, this we have already know this relationship exists. Okay, so because 1 over F is R, so we take the 1 over 1 minus, not 1 over 1 minus F is R, reliability function. So RUT actually equals to RST over F. Now FUT over RUT actually equals to 1 over AF, because we just got this relationship over RS. So that's why HUT, the failure rate at a use condition, is actually the failure rate 1 over AF, the failure rate at T over F. Okay. So in other words, the failure rate here at this time is much bigger, because you need to divide by AF factor, then you got HU. So the failure rate here is smaller, and however, failure rate here is much larger because it's under stressed condition. Now, let's assume our failure, the lifetime distribution follows the exponential distribution. Now, under the exponential distribution, if we have acceleration, then what will be the relation? So this is this part. So otherwise, in other words, if we have this relationship, we can assume this t follows exponential distribution. The lifetime of the product, they can follow the exponential distribution, Weightable distribution, or log normal distribution. Some of you might ask, oh, what kind of distribution should I use for my lifetime? This actually depends on the data. If you have a lot of data, you can plot the you can do the test, use the probability plotting. For example, the normal probability plotting. You can assume the lifetime follow normal distribution. You can also assume the follow exponential, so you can use exponential probability plotting. Okay, we're going to talk about the probability plotting in the next later. But based on the data, you can test what kind of distribution the lifetime follows. And you can also visually just plot a histogram to see what kind of distribution it follows. But some of the distributions, they are very similar to each other under different parameter settings. So that's why we need a statistical test, like the chi-square goodness of fit test, or the that's called a quantitative test. The other one is called a graphical test. Graphical test is a probability plotting. There are different kinds of probability plotting: normal probability plotting, exponential probability plotting, log normal probability plotting, Weightable probability plotting. We're going to talk about those probability plotting later, but let's first assume the lifetime follows the exponential distribution. So high stress condition, we do the experiments, we got the data, we got the failure time, and we want to see whether we want to assume the failure time follows the exponential lifetime distribution, and the failure rate is lambda s. So at the stress condition, if we assume this is a lambda s, then we got this distribution. This is a CDF function. Because we have this relationship FUT equals to FST over AF. Now we can get the CDF function under normal use condition, because although you did an experiment at a stress condition, but your interest is at the normal use condition. You want to see the distribution or lifetime distribution under the normal use condition. So FST over AF. So if we put it over here, then lambda U equals to, this is a failure rate because exponential distribution with a constant failure rate. And at lambda U equals to lambda S, this is the failure rate under stress condition. So this failure rate is much bigger. So you divide by AF, you got the failure rate at a normal use condition. So CDF at use condition remain exponential. So this is still an exponential distribution, but just with a different lambda U. Lambda U is much smaller. So when time is multiplied by an acceleration factor, failure rate is reduced by dividing by AF. So you see, the time is actually much bigger because if you fail at a stress condition, you are actually much faster fail, right? So you multiply by an acceleration factor, you got a normal use time to failure. But the failure rate is smaller, okay? And then this failure rate at stress condition is much bigger. Now let's look at an example. So a component is for the reliability test. So 125 degrees, you got a data. And then the exponential distribution, this follows exponential distribution, and the mean time to failure. Mean time to failure is 1 over lambda. So if we know mean time to failure, then we know the lambda. 32 degrees is a typical use temperature. Acceleration factor is 35 between these two factors. Now, what is the failure rate at a use condition? And what percentage of component will fail before the end of expected use life of 40,000? You see here, this is 1 over lambda S, okay? So mean time to failure at a use condition equals to acceleration factor times mean time to failure at stress condition, because this is accelerated. That means this time is happen much faster. So you times the factor, you got the mean time to failure at a use condition. So 35 multiplied by 45,000, you got a 157,500. So lambda U is equals to 1 over this. So it's actually 0.635% per K. So FU 40,000, because normally we want to see what a percentage, right? Equals to 1 minus exponential minus lambda U times 40,000. So what we get is 22.4%. So it's there's about 24.4% component will fail before the end of the useful life. Now, suppose in the previous example, the requirement was no more than 10% of the component fail by the end of the use life at a use condition. So what acceleration factor do we need in order to achieve this reliability? Okay. So stress condition 45,000, lambda S is this one. So let's assume FU equals to FS. So this is the use condition, the CDF function equals to 1 minus lambda exponential minus lambda S T over AF. Now let's put the 40,000 over here, and we keep, because we want to derive AF, but we want to see no more than 10%, then let's just put it equals to 10%. Then let's derive it. And we found that AF should be 84.28. This should be our AF, acceleration factor. Okay, so far we discussed the if the lifetime follows the exponential distribution. Now let's have a look at if the lifetime follows the Weightable distribution. So high stress, you do experiments, you get data, and you want to see whether the failure times follows the Weightable distribution. So what is the Weightable distribution? This is the Weightable distribution. Weightable distribution has two parameters, CS and MS. MS is a shape parameter. CS is a characteristic life. So this is a distribution function. We know that FU equals to FT equals to FS T over AF. So we just, because we know FS already, so we put this T over AF in the equation. So we got this factor. So for Weightable distribution, the change The characteristic life is actually multiplied by AF, but the shape parameter doesn't change. So if the lifetime distribution, one level of stress is Weightable, then the lifetime distribution and other level of stress is also Weightable distribution, assuming that we have a linear acceleration factor. Oh, this is a very nice property. So if the shape parameter for different stress is different, then either we don't have linear acceleration or Weightable is the wrong model. Now, if you got data, how do you see whether data follow Weightable distribution? So here is the Weightable probability plotting. So if you have the FT and the 1 minus, this is a CDF function for Weightable. So if we want to do the probability plotting, just as the normal probability plotting, we want to generate some linear, a straight line. So how do we generate a straight line? We are going to do the linear rectification. So we're going to move the 1 minus f to this side, and then take log. And then what we get is the log t. And those are the parameters, log t. And this is my response variable. And this is my, for example, for linear regression, this is my y, this is x, and this is ax plus b. So m will become, if you do the linear rectification, because this is a nonlinear function, right? Nonlinear equation. So you do the log, you convert this nonlinear equation into a linear equation. Linear equation, it will become log minus log 1 minus ft, and equals to the ax plus b. So this whole term minus m log c becomes the intercept. M becomes the slope. So if this and if we plot this versus log t, if it follows a straight line, then this will become a Weightable distribution. Because Cu equals to AF times CS, if the data follows the Weightable distribution, Mu equals to Ms, multiple stress condition. So approximately you see Cu is right here. So M doesn't change. So if we do the multiple, the probability plotting for multiple stress data, they should be approximately parallel lines with different intercept, because if you do the linear acceleration, it only changes the C, right? M doesn't change. So the intercept, because you have log C term over here, approximate parallel lines with different intercept. So if we look at the failure rate, this is a failure rate at a stress condition. At a use condition, this is at the use condition. So it equals to, because the Cu equals to AF times CS, right? So what we're going to get is the HUT equals to 1 over AF MS HST, and MU equals to MS. So this is because we derived this before. Am I making sense? This is Weightable probability plotting. We have a nonlinear equation. We do the rectification, convert the nonlinear equation to a linear equation, because this becomes x, this becomes y equals to ax plus b. And then we can, once you draw the plot, you can check based on the data, you can fit the model, you can get the parameters. So you can estimate the slope, estimate the intercept from the data. I'm going to show you a demo, MATLAB demo from this example 7.2. I'm going to show you how to do the Weightable probability plotting in MATLAB. Now, let's assume we have another, the lifetime distribution is log normal. That means if we have high stress experiments, we got the failure time and all the data. Let's see whether it follows log normal distribution. So what is a log normal distribution? So this, we directly use log normal distribution. If you don't know log normal distribution, you can go to the Wikipedia, or you just search log normal distribution. It will show you different kind of log normal distribution. So if a random variable is log normally distributed, that means x is log normal distributed. Then if you take log of x, this will become normally distributed. So if you have x log normal distribution, if you take log, it will become normally distributed.
The same for CDF function. CDF function, because log x is normally distributed, then so that's why it is called log normal, because once you take the log, it becomes normal. So that's why they name it log normal. So you have an x, you take the log, become normal. Then for the x, fxx, it will become log x minus mu over sigma. Okay, so this is the CDF function. This is the PDF function. And this mu, sometimes we use, let me show you the T15 log normal. You see, this is log T. T is log normal, and log T is normal. Okay, then log T and T50, you see T50, T50 here. T50, log T50 is the mean, mu. You see, log T50 is the mu, like x minus mu divided by sigma. Then you convert it to the standard normal distribution. Okay, so if time to failure TF has a log normal distribution, then the natural logarithm of time of failure has a normal distribution with mean mu equals to log T50 and a standard deviation sigma. So if we assume mu equals to log T50, this actually makes log normal data very convenient to work with. Just take lateral logarithm of all the failure times and analyze censoring and all the failure times and censoring times and analyze the resulting normal data. Later on, convert it back to the real time and log normal parameter, use sigma as the log normal shape and T50 exponential mu as the median scale parameter. So this is T50 is actually a median scale parameter. So that's why here, if the failure time under stress condition follow log normal distribution, then fst equals to phi. This is log t minus log t50 s, because this is under stress condition, divided by sigma s. This is also what we have here, fts, fst, right? fst equals to log t minus log t50 over sigma. Why I use the you see the division here, because log a over b equals to log a minus log b. Okay, so this is stress condition, it follows log normal distribution. Then at a use condition, we know this equation is satisfied, right? Then what we are going to do is plug in this into this equation. Then what we get is, you see this shape parameter doesn't change, the same, and the scale parameter actually T50s is multiplied by AF is actually T50U at the normal use condition. So true linear acceleration does not change the type of distribution or the shape parameter. Only the scale parameter is multiplied by the acceleration factor between two stresses for log normal distribution. So if we have log normal distribution, we know that log t follows the normal distribution. Then we know z equals to log t minus log t50 phi, but z equals to phi inverse f. So we put this over here, then we can see log t equals to sigma phi inverse f plus log t50. Therefore, you see this is a nonlinear equation, but if we do the linear rectification, so this will become our y, this will become our x, y equals to ax plus b. So this sigma becomes our slope. Log t50 becomes the intercept. Therefore, different stress will give nearly parallel lines if plotted together, but with different interceptions. And some of you may say how to estimate f. So for exact observations censored out of a sample n, we know exact failure times known. So you can sort them from the smallest to the largest. Then FTI equals to I minus 0.3 divided by n plus 0.4. So one can estimate the F. And this is exact observation. You know exact failure time, so you can do this. But readout data, with readout times, that means at a particular time you read how many failed. So f will equals to total failures by this time, then divided by starting sample size. This will be the f. So those are the two different ways to estimate f. So up to now, we finished all the theoretical part of the physical acceleration model. And in the next lecture, I'm going to show you two demos on Weightable probability plotting and also the log normal probability plotting, and also show you these two examples and how can we use data to draw the probability plot and also estimate those parameters like characteristic life and shape parameters. For log normal distribution, we have scale parameters and shape parameters.